Okay. Well, if you ever wanted to know how driverless cars work, well, this lecture is for you. We're going to talk about how machine learning is specifically used to create driverless cars. So all the stuff we learned about supervised, unsupervised learning, and the various techniques, we're going to sort of go through again a little bit and show you how this all works. So here we have a Lexus outfitted with a LiDAR unit, and it's got some cameras and it's constantly spinning, and it uses laser beams to generate a 360-degree image of the car's surroundings. And the cameras, they use parallax from multiple images to find the distance to various objects. So a beam of light is sent out, it measures the time to get back, and you know how far the car is from the surrounding object. The camera also detects things like traffic lights, signs, and help recognize moving objects like pedestrians and bicyclists. Talk about how exactly these objects are recognized. And they also have some sensors here, radar sensors, that measure the distance from the car to obstacles. So in terms of data capture, the sensors gather data on all nearby objects, their size, rate of speed, categorize the objects as cyclists or pedestrians or other cars and objects based on how likely they are to behave. And that's misleading because a lot of the labeling and annotation is done by hand, but that's nonetheless, it still needs to be done. As I said, with these LiDAR systems, they illuminate the car's surroundings. So they create what's known as point clouds. And from those point clouds, someone has to provide 3D annotations as to what the objects are in the scene. And we're going to show you various videos, various companies, how they do that. The reason these videos have to be annotated, why the LiDAR data is annotated, because it provides accurate georeference coordinates that are used to replicate really the reality of a car's surroundings. So without that, you don't know, the car doesn't know what it's seeing and can't react safely to what's in the environment. Here's an example. So we have a scene, we have data gathered from our sensors, and we're going to have to annotate this image with boxes, surrounding boxes they're called. So here you have some pink boxes that annotate that this is a vehicle. These yellow boxes here indicate that pedestrians. This green fence here indicates locations where the car may slow down because it's a curve. Red fences are locations where the car will need to stop. So somehow all this information, semantic information, needs to be annotated. How's that done? Well, we'll talk a little bit about that. As I said, you have some scene, you have some objects from the sensors in the camera, and you want to do is create bounding boxes. That's step one. Step two is to label these boxes as to what they are. Most of the time has to be done by hand. It can also be automated somewhat, and I'll describe that shortly. What we'd like to do is use machine learning to help us as much as possible. So the raw images contain objects, as I said, road signs, traffic lights, or moving objects like people. So what we'd like to do is take the sensor's raw data and deliver it back with bounding boxes and labels that accurately categorize and identify those objects. So we need to do this both for recognition and decision making. Well, the bounding boxes, I'm sorry to say, is done by humans, and it's very time consuming. How time consuming? Well, for every 1 hour driven, it takes approximately 800 human hours to label. So that's pretty amazing. So can this be automated? Well, I think it can. You remember we talked about semi-supervised learning. That's the case where the teacher provides some of the input, not all the inputs. So if somehow we can provide some of the labels for the objects in the scene and then bootstrap the system using supervised learning, maybe we can learn the rest. And there's a company actually trying to do this called Drive.ai. We'll see how that turns out, because doing this by hand is very time consuming. We'll show you what Google does too shortly. Once you label the images, these images are then used to teach the systems how to recognize the objects and how to decide on the appropriate response. So how's that done? So what you'd like to do, build another classifier on top of this one. So the first classifier identifies the image. The second one predicts the action that the car should take based on what it sees. Okay, So one sample classifier could be, you can create a neural network. And these are usually deep neural networks. And we'll show you that shortly. Let's take a simple one. Has got 3 digitized outputs: the steering wheel turn, the brake pressure, and the gas pedal pressure. What you can do is the system can be trained to mimic a human's driver's steering, braking and gas in response to visual input over many thousand hours of training. So you have to give it thousands of hours of training, and then you can mimic the steering and braking and gas. So if you do this, the neural net or whatever underlying structure you use, underlying architecture, will learn to match the human's responses to very high levels of accuracy after seeing lots and lots of miles of training. As one example, if the region labeled car in the center of a frame gets larger in a subsequent frame, you're probably going faster than the car in front of you, and the action should be to apply the brake. So the network will learn this if it's got lots and lots of examples. We talk a little bit about annotation here. You have some scene, and then you need to label this scene. So you go from here to here, and there are several ways of doing this. There are actually 4. So one is you assign to each pixel corresponding to the object so you assign a label to each pixel corresponding to the object which the pixel belongs. That's very time consuming. A second level, which is more complicated, is to provide sort of semantic understanding, which is providing enriched data for contextual situations. So it's not just the objects, but you're providing context. So you're taking image understanding from low-level features to high-level semantics by identifying the objects and the events, providing situational understanding. So you have, a pedestrian walking in a crosswalk. There's a curb here. So it's got to understand the whole scene. If you look at the cost of doing this, so we talked about bounding box. The time commit is the lowest. Well, it's still pretty expensive. We said for every hour of driving, you need 800 human hours. The precision is pretty good. For assigning a label to each pixel, that's more expensive. The precision's better. Another way is to assign polygons to represent the objects. And the last, which we talked about, is the most expensive, providing semantic segmentation, which is situational awareness. That's also very expensive, but it leaves the best precision. You understand exactly what's going on in the scene. Okay, so here's going to show a video of an early semantic segmentation of a scene done several years ago. So you have this running, you can see it generates about 8 different categories: sky, tree, building, road, grass, water, and object. This is an old video, but I have a new one I'll show you shortly. It's still pretty neat. So this is in real time. You see the scene below here, and then you see the objects that are being labeled. I should mention that a video that shows the point clouds that are created from the LiDAR system. So you can see here, just a brief, here are the point clouds. Just another illustration of what's seen and how much semantic augmentation really needs to be done. So I'm going to talk about another approach to using machine learning for self-driving cars. Let's talk about NVIDIA's end-to-end approach. Okay, what do we mean by end-to-end approach? So that means we're mapping raw pixels from the camera into steering command. First of all, this work was inspired by Dean Pomerleau, who I actually met in 1988 at the Connectionist Summer School. He was the first person to develop the first self-driving car, and so it's about 26 years ago, and you can see how far we've come. So when he did this, 1988, 87, as part of his, his PhD thesis, his car was actually on the road. The mean distance between crashes was about 20 meters. So he used a similar approach to what's being used today, but with the advent of these deep neural networks and increased computing power, the systems got a lot better. So how does this work? So NVIDIA, they have some cameras. The imagers are fed in. Let's ignore this random shift and rotation stuff. They're fed into a convolutional neural network, and we'll talk about that network in a second. This network computes a steering command, and that's compared to the desired steering command that comes in from a recorded video. So video comes in, a recorded steering command. Ignore this for a second. This is what should be done. This is what the network thinks should be done. It computes the difference, the error between the actual command and the one computed by the network. The error is then, using backpropagation, which is a technique for weight adjustment, goes back into the neural network, and this iterates. And the idea is the network keeps being adjusted until the output comes closer to the desired output. So that's training this convolutional neural network. Problem is the network needs to learn how to recover from mistakes. So otherwise the car will slowly drift off the road. So that's the reason for this adjust for shift and rotation. So what you need to do is the training data needs to be augmented with additional images that show the car in different shifts from the center of the lane and rotations from the direction of the road. So if you don't do that, the car never learns to recover from mistakes. So you have some additional lane positions and lane shifts that's fed in to make the situation the car more adaptive. And this random shift and rotation simulates that. So you randomly shift where the car is in the lane and let the system learn all possible variations. So training data needs to be collected, a lot of it. You need to collect data in all kinds of conditions: clear conditions, cloudy, foggy, snowy, rainy, day and night. Okay, and as I said, you need to augment the data. And we talked about adding additional shifts and rotations to teach the network how to recover from a poor position or orientation. Now, once that's all done, so after you've trained the neural network, this network is now loaded, software is loaded into the computer on the car, center camera is recording, so the data is fed into this neural network, and out comes the network computing steering command, how the car should steer. And that's fed into this drive-by wire interface, and that's how the car drives. Okay, so it seems all pretty nice, right? No problems. The authors of this study, they also point out that you really need 3D scene knowledge. And the reason is, so you're driving on a highway, and you need to assume that all the points below the horizon are on flat ground. And it assumes all points above the horizon are infinitely far away. And the author is saying that this works fine for flat terrain, but it introduces distortions for objects that stick above the ground, such as cars, poles, trees, and buildings. They claim that these distortions don't provide a big problem, and that the steering label for transformed images is adjusted so the vehicle can do the right thing and orient itself in about 2 seconds. But I would argue that if you're in an urban setting, that you're going to really need to augment the scenes with more information about what's going on in the scene. Okay, here is the CNN architecture, the convolutional neural net. You can see it's very complex. So it's got 5 convolutional layers. 1, 2, 3, 4, 5. Actually, 1, 2, 3, 4, 5. And these convolutional maps extract features. And you remember the depth of the maps, they act as filters which improve the recognition of unknown scenes. So you have very deep convolutional nets. You have 5 of them. You also have 3 fully interconnected layers here that sit on top of the convolutional net. They're used for controlling the steering. You have some normalization layer down here, which normalizes the data, and you have an input layer and the output, which is the command to steer. So you can see this network has 27 million connections and about 250,000 parameters. So when Dean Parmelee was doing this in 1987, 1988, there just wasn't the compute power around to do this kind of computation needed to train these networks. Even though deep neural networks, they weren't called that back then. They usually had 3-layer networks with 1 hidden layer, and sometimes people are operating with 2 or 3 hidden layers, but you couldn't actually do this then. Just the compute power, the graphical processing units didn't exist to do this. So here's an example of what this thing learns. So this top image is what the CNN, the convolutional neural net, actually sees. This is a subset of the camera image sent to the CNN. So right here, that's what it's partially seeing. Bottom left, right here, this picture, that's the activation of the first layer feature maps. Bottom right, this picture here, is the activation of the second layer feature map. So here's the first layer, here's the second layer feature map. And you can see that the architecture's learned some useful road features on its own with only the human steering angle as training signal. So the network was never trained to detect the outlines of the roads, and it's partially done that here. Okay, here's another image. This is an example image with no road. The activations of the first 2 feature maps appear to contain mostly noise. So that's the first level feature map. Here's the second. So in this case, the CNN doesn't recognize any useful features in this image. So it's got to learn to recognize useful stuff from not useful stuff. So it's pretty amazing, pretty complex architecture. Okay, so let me show you a video of NVIDIA's autonomous car in action. This was done in 2016. You're going to see that here's the car in action. In the first 32 seconds of the video, you're going to see things were a little rough for the deep learning car as it hits the road. It crashes over cones, crashes into trash cans. It gets confused by several roads, and human intervention was often required. I'll let this roll. So this is a few months later. This is after 3,000 miles of driving. Now compare this to what Google's done. Google's used 2 million miles of autonomously driven cars. So this is just using 3,000 miles of training. You saw a couple of months before this, the thing was crashing all over the place. So it's improved quite a bit. Okay, so much for fun. Let's talk about some potential problems. Well, building detailed 3D maps of each new city needs. So when Google goes into a new city or a new location, they have to build 3D map of the city. They have to annotate the data, and I'll show you that in the next video. That's non-trivial, requires a lot of work. So as we said, you need to categorize different features, intersections, driveways, fire hydrants. That's the first problem. The second problem, driving requires complex social interactions. So, like what? Well, there's several things. One is the cars need to understand the environment around them. They need to understand why the people they encounter on the road are behaving the way they are. They have to decide how to respond. So you come to a four-way stop, what do? You really have to understand the intent of the other drivers around you to navigate one of those things. And I don't know if you live in Massachusetts like I do, when you have these rotaries down on the Cape, try to navigate that with one of these autonomous cars. You really need to understand the intent of the other driver. And so the fourth one is communicating with other people. So another example of driving that requires social interactions, think about making left turns. These are really hard. It's hard for humans. Why? Well, you need to understand the intent of the other driver. So good luck with getting machine learning algorithms to do this. So just as, I don't know if you're aware of this, but UPS requires its drivers to avoid left turns. And so they map out all their routes to take right turns, because it's shown that making left turns, the cars are more likely to get into an accident. Another instance of complex social interactions. What about recognizing hand signals, for instance, from cyclists or even bicyclists? That's not easy to recognize what they're doing. What about bad weather? In bad weather, much like our eyes, the car senses don't work as well in fog or rain or snow. And what's more, most of the companies that are testing these cars are testing them in benign climates like Mountain View, California, not up in the Colorado Rockies or in Boston, where I live, where the weather can be terrible in the winter. What about recognizing broken lights? Well, it may have been trained to recognize a light. I suppose it can learn to recognize a broken light and figure out what to do, but I don't think that's so easy. Finally, what type of regulations do we need to ensure that these cars are going to be driven safely? Might need a whole different set of regulations. These are more political problems than machine learning problems. But just to give you a point of reference, drivers in the U.S. currently get into fatal accidents at a rate of about 1 for every 100 million miles driven. So that's a pretty high standard for these machine learning algorithms to get at that level of accuracy. I'll mention also that another use where we can use unsupervised learning here is in terms of recognizing, for instance, stop signs. They come in all different shapes. Well, they're all octagonal, but the red and white, the red could be faded. There could be trees precluding or occluding the view of the stop sign. So it may be possible to help in annotating these objects and recognize these objects, to use unsupervised learning, do the grouping and find the inherent features so it can recognize what a stop sign is. Okay, we've seen NVIDIA's end-to-end autonomous vehicle. Let's take a look at Google's autonomous vehicle. Remember, NVIDIA was trained only on 3,000 miles of driving, whereas Google's been trained on almost 2 million miles of driving. So you remember this picture I showed a little while back, how objects are categorized. Well, we're going to show a video where Google, remember, when they go into a new place, a new city or town, they have to drive through the city, create a detailed 3D map, and then they have to go over the video and mark all the objects, as you see here. So there's a lot of manual work that's being done to mark the intersections, the obstructions, etc. Okay, here's the video.
Help the vehicle to recognize and navigate through construction zones. Our sensors spot the orange signs and cones early to alert the car of the lane blockage ahead, and we can change lanes safely. You'll also notice the vehicle typically moves to keep a safe distance away from large obstacles, like this truck stopped on the side of the road. Now we're approaching a railroad crossing, which requires special care. Notice the red fence and railroad sign that appears to the computer as we approach the intersection. This means that we'll wait until the tracks are clear of other vehicles before proceeding. Our cars treat cyclists as a special category of moving object. Watch in this example, when the cyclist holds up his arm, our software detects the hand signal and predicts his movement into our lane. The car knows to continue yielding to the cyclist passing by, even when he changes his mind, multiple times. So now what you'll see is our vehicle at a busy intersection. Here the cars are represented by pink boxes, and the cyclists and pedestrians are the red and yellow boxes. Now notice the boxes moving past us. It's a cyclist and pedestrian's turn to go. The red and green fences indicate that the car will stop and wait until the path is clear. We even detect the cyclist approaching from behind and wait until they've passed. Once the cyclist has gone by, the vehicle determines that it's safe to turn. We still have more work to do, but it's fun to see how many situations we can now handle smoothly and naturally. See you on the road.
Okay, we've just seen the video of Google's autonomous driving vehicle. And you remember we talked about a few slides back that driving requires complex social interactions. We talked about the difficulty of making left turns and recognizing hand signals of cyclists, because you have to recognize the person's intent. As you can see in that video, Google does a very nice job of solving this problem. At least in this case, there's still a lot more work to be done, but nonetheless, they did a good job. One more fun thing. I don't know if those of you are lovers of Star Trek, but if you never heard about it, take a look at Star Trek: The Next Generation. Specifically, this episode, TNG 142 Q Who. It talks about the Borg, which are cybernetic life form that are thousands of years old, which are part organic and part artificial life. And they're born humanoid. They're immediately implanted with biochips that link their brains to a collective unconsciousness, which is communicated by some subspace frequency. Well, what's neat about this, the collective unconsciousness is experienced by the Borg as thousands of voices. So they're collectively aware, but they're not aware of themselves as separate individuals. Well, why does this matter? Well, let's suppose in not too distant future, we're going to have driverless cars and they're all going to be operating. Well, how can we update the intelligence of these cars? They're all in a network like the Borg. They're not collectively aware, but I think in the future they will be collectively aware and aware of themselves not only separate, but as part of the network. So I think now you can automatically up the intelligence of a car by the experience of other cars in the network. So that's going to be pretty cool. So you can take all the good driving experience of others, use that to update the intelligence of your car. Pretty neat. Okay, that's the end of this lecture.